Good morning, good afternoon, wherever you happen to be. Welcome to Why Ferrocene. My name is Jonathan Pallant. I'm coming from a slightly damp Cambridge, England this morning. It is, as we would say, raining cats and dogs outside. Excuse my slightly disheveled appearance. We are here for Why Ferrocene, a brief discussion about what ferrocene is and what it isn't. I'm so glad you could join us today. This is going to be a sort of session in 3 parts. We're going to start off with some slides. I've got some things to tell you about ferrocene and the qualification process we've been through. We're then going to do a live demo. And that is going to involve me writing pretty much from scratch a bare metal 64-bit ARM binary, because as we will see, that is the supported target for the first release of ferrocene. I may cheat along the way. There may be some copy and paste. And then we're going to finish up with a Q&A. If you're in StreamYard, you can leave comments through there. If you're on YouTube and you are logged in with a Google account, you can leave comments on the YouTube stream, and we will see those as well. Feel free to leave comments and questions as we go through. If they're relevant to the topic we're discussing, I may answer them there and then. Otherwise, I may save those to the Q&A at the end. Actually, we've got 20 people signed in at the moment. So glad you could join us. Let's kick off. And I now do... a little bit of talkie while I go and click share screen and entire screen, and I make sure I go and select the correct window. As a full-time trainer, I do this a lot. We will do that. Oh, and I should turn off the banner. There we go. So I've got a few slide decks, few short slide decks to take you through today. Ferrous Systems makes all of its training material open source. So these slides live in this GitHub repository, ferroussystems.com. GitHub.com/ferroussystems/yferrocene. So you can go and get the slides if you want the rendered HTML versions. They're going to be here in the release area. You can just download the zip with all of the slides in. Someone did comment to me, oh, you don't have real slides, only HTML pages. Yes, where I come from, HTML pages are real slides. But okay, so you can download those and follow through later on if you want. This session is being streamed to YouTube, so you can come back to StreamYard or you can come back to YouTube and catch up at a later date. Okay, let's get stuck in with our first deck. And we're just explain that Ferrocene is just Rust. Have we been up? We didn't write a new toolchain. This is not a new qualified toolchain. It is really just the upstream Rust toolchain, and we have taken it through the qualification process. So it is the Rust you know and love. It's not a subset of the language. The Rust you're familiar with, that's what you get when you use Ferrocene. And one of our goals here was to make sure that Ferrocene does not diverge from what we call upstream. By upstream, we mean the Rust project, the open source project that produces the Rust compiler. So we don't want the standard library to change, and we don't want the compiler to change. We don't want to be some special Rust subset that's useful for safety critical. Rust is a great language, and you should be able to have all of it. And so that's our goal, is to make sure that Ferrocene tracks upstream. It may maintain differences to upstream, but it will not diverge. Those differences should not grow over time. And some people have said to us, well, I don't know if that's possible. How could you track upstream? And I think we can point to a lot of evidence to say it works. We have been doing it since 2021. We've been taking changes from upstream, and we've been merging them into our tree. And then every day, every few days, we go and do the merges, and we bring the source code from upstream into our tree. So the process works. And of course, when we do that, we then run it through the full test and verification suite as well. During this process, unsurprisingly, there were some things in the Rust toolchain that needed fixing, some things we found, some things that didn't quite work for us. And I guess there was a question at that point whether we were going to keep those changes to ourselves or if we were just going to push them upstream. And it's not a question we had to think about very long, because we're an open source company. So all of the changes we had to make to the open source toolchain to get it through qualification, we sent them upstream. You can see some examples of the pull requests here. If I click on one of these at random, ignore core alloc and tests that require unwinding when panic equals abort. So we were running the test suite, perhaps a slightly different way to the way upstream does it. And some of the tests needed some changes. And so we just sent them upstream. That's how we've managed to keep the set of things that are different in Ferrocene to an absolute minimum. There's no secret sauce here. This is just making the compiler better. So we might as well make the compiler better for everyone. This then has some really interesting knock-on effects. I think there was an issue where some of the tests weren't being executed because they hadn't been annotated correctly. So we fixed that, and then the test started running, and then we were able to find other things that were wrong, and then we committed fixes for those. So this kind of sharing of the work is just a good thing for the project, and it's a good thing for Ferrocene, and I think it's a good thing for all of the communities that are interested in Rust. So what do we have in Ferrocene that doesn't exist in the upstream project? Well, the first thing is support for Lynx OS 178. This is a proprietary safety critical real-time operating system focused on aviation markets. I think it's used in the F-35, but it requires a proprietary C compiler in order to use it, and you can't get Linux OS 178 unless you buy a copy. You know, it's a commercial proprietary product aimed at a certain market, so it doesn't really make sense to send that upstream. We could, if someone upstream said, actually, no, we could look after that. Sure, but for now, that doesn't make sense to put into the upstream product. There's also one feature that we need that upstream I don't have yet, so we've put it in our tree, and we've got a pull request for that, and there will be discussions. And upstream may do that; they may do something similar. So that's another difference that we have at the moment. And the other difference between Ferrocene and Rust is the build system and the build and test infrastructure, I should say. So the open source upstream project have their CI system designed to do a certain job, make release binaries available free of charge. Ours needs to do a different job. We're testing different targets, and we need to produce documentation and traceability matrices with the test logs and all of that kind of stuff. So our build and test infrastructure is different, and we keep that in our tree. And having these two build and test sets of infrastructure, these two continuous integration systems, is, we think, a good thing, because it can only help make the project more robust. Having it built with two different CI pipelines mean that you can't rely on assumptions about how the CI pipeline is set up, because we set ours up different to the way the upstream project does. And I'm sure that's found some issues, and that's been a good thing. It makes the project more robust for other people who wish to build it themselves. There's no magic going on in the CI pipeline because we've got two of them, and we show that they both work. And we have certain artifacts we need for the qualification process, which we will talk about a little bit later. So that is a little bit about what Ferrocene is. It's just Rust. Let's now talk a little bit about upstream versus downstream. And I want to do this using an analogy. So many of you will be familiar with the idea of an enterprise Linux distribution. We don't need to name any companies here, but you can imagine the kinds of things I'm talking about. And in this model, the enterprise Linux distributions are a downstream of the Linux kernel. The Linux kernel is the upstream. So the Linux kernel makes kernel releases. They make them available as source code. And the enterprise Linux vendor then takes those releases, takes that source code. They will run it through a test suite. They will add any required fixes or any backports. And they may then contribute those back up. They will publish their version as open source, because that's what the Linux kernel license requires. And then the enterprise Linux vendor, their job is to sell binaries, right? So they will sell their customers binaries, and they will offer a long-term support package alongside that. And I sort of see Ferrocene as following a pretty similar model. Ferrocene is a downstream of the Rust project. The Rust project make releases of their toolchain. They happen to make them as both binary and source releases. But we take the source code and we run the test suite. It's actually the same test suite the upstream project has, but modified slightly, looking at slightly different targets, perhaps. We will apply fixes and backports. We publish as open source. The license of the Rust project does not require us to do this. It is Apache 2 or MIT. We could have kept that all as secret source code, but we chose not to. So we publish our version as open source, and then we sell our customers binaries along with a long-term support package. I think it's a fairly familiar model. I think businesses are going to be fairly comfortable with the idea of saying, here's an open source thing, but here's a place where I can pay a small amount of money and I can get some support and some reassurance that everything is going to work, because it's, if it's something your business depends on, that makes sense. And so, yes, Ferrocene is open source. We think It is the world's first open source qualified toolchain. To be fair, there are toolchains which are qualified and are based on an open source upstream, but I'm not sure of anyone who is publishing the source code for the qualified version, including the test suite and the matrices that link the spec to the tests and all of that kind of stuff, and the source code for the qualification documents. If anyone has any examples to prove that I'm wrong, please do share them in the comments or reach out afterwards. I would be delighted to know that other people are doing this as well. But as far as we can tell, we're the first people to go, well, you know what, we'll just make the whole lot open source. You can try before you buy. And we think it makes sense as an open source company building on an open source project. So we do offer long-term support that's available on a commercial basis. And we're going to talk about long-term support later on. But there's your first two key takeaways. Ferrocene is open source and Ferrocene has long-term support available. So we talked about it being a downstream of an upstream. Now let's get into a little bit about the supported host platforms and the target platforms. So a little clarification here. When we say host platform, we mean the machine you are running the compiler on, which also has to compile code for itself because we have procedural macros and build scripts which execute at compile time. So the host ends up being a target as well. That's not necessarily the case with C compilation. But yeah, here, Rust is a cross compiler by default, and the host is a target. And when we talk about a host platform, we are going to be talking about a combination of CPU architecture, the operating system, and the ABI, the application binary interface, the set of rules that a binary must follow on a given platform about when you call a function, this is where the arguments go in these registers or in that place on the stack, and here's where the return value goes, and all these kinds of rules. This matters because some platforms like Windows, there are two ABIs available. There's the Microsoft Visual C and the GNU ABIs, and that happens on some other platforms as well. glibc versus muzzle C if you're a Linux person. So that's what we're going to talk about in terms of the host platform. It's a fairly simple list for now. There is just one, x86-64 unknown Linux GNU. Yeah, target triples are not really user-facing documentation. They are unambiguous, but they're not necessarily easy to parse. So let's just dig into that. So what we mean by this is Linux using glibc, that's the GNU part, on a computer made by anybody, that's the unknown part, unknown manufacturer. You can imagine in the olden days, that would be IBM or Sun or Apple or whatever. And x86-64 is just 64-bit Intel or 64-bit AMD. So it's kind of common or garden. 64-bit Linux machine is our supported host for now. We do want to add more hosts later. We'll get onto that. And for qualification purposes, we had to pick a specific Linux distribution, specific version of glibc and GCC and the kernel and so on. And we went with Ubuntu 18.04. Now, we are aware that is not the latest version. There is 2004 and 2204 in terms of LTS. But we were driven by the needs of our first client. They're a big Japanese automaker that I can't name. But they said, this is the platform we use for building software. So this is the platform we want Ferrocene to run on. So that's where we've started with. And so 2306, Ferrocene release 2306 has been qualified on 1804 using GCC 7.5, which is the compiler that platform comes with. And why do we need GCC? Well, we use it as a linker. We use it as a linker because when you're linking for host as a target, GCC knows where the C libraries live. If we used some other linker, we'd have to teach it where everything lives on disk. Your operating system linker already knows this stuff. So Ubuntu 18.04 is our supported platform. It should run on any Intel 64-bit Linux system. Obviously, if you diverge from what we say in the safety manual in terms of supported platforms, the signed qualification documents are going to be less useful to you. But we know people want other versions of Ubuntu. They want to think about Red Hat. They want us to think about SUSE. They want us to think about Debian. They want us to think about Windows. They want us to think about Mac OS. Will be driven by clients' needs on this. If you've got some specific examples, platforms you want to run Ferrocene on, leave us a comment right now. Please reach out via the website. It's ferrous-systems.com. Go to the contact page and you can reach out there, and our sales team will be very happy to talk to you about your specific needs. Because, yeah, you may go, what about my favorite host? If Rust already runs on that platform, we're going to have a fairly straightforward job. It's a case of setting up the CI infrastructure and running the test suite. If you want it to run on an Apple machine, for technical and legal reasons, we then need Apple machines in CI to do the build and run the test suite. I believe GitHub now make M1 Max available to GitHub Actions. I'm not sure if our CI provider does yet. So Apple machines might be interesting. If you need them, do reach out and tell us, and then we can look at that. Windows is fairly high on our list because we are aware many embedded developers are primarily Windows people. That was a job I used to have not so long ago, so we understand. But so if Rust already runs on the platform, elevating that platform to Ferrocene supported level is a piece of work. We can do that. And if Rust doesn't already run on your favorite platform, yeah, get in touch. Maybe we can port it. I would be very interested to know what platforms you might want to run Rust or Ferrocene on where Rust doesn't currently run. So there we go. So that's Ferrocene as a host. Let's talk about Ferrocene's supported targets next. And this is the machine that runs the compiled binaries. So we do the build, and then if it's an embedded system, we flash the firmware, we send the DFU file over USB, we send the diff file up to the firmware distribution cloud service, whatever it happens to be. But this is the machine that's going to run our compiled code. And again, CPU architecture, operating system, and ABI. And again, it's a fairly short list to start with version 2306. We have the host platform, as we discussed, and we have AArch 64 unknown none. That's a bit of word soup. Let's break that down. You can think of that as being 64-bit ARM on bare metal. If you are an ARM enthusiast or an ARM expert, you may realize that is not specific enough. So let me say it is A64 instructions running on an ARM v8A processor in AArch 64 mode. Yeah, if you're not an ARM expert, sorry. The ARM platform is, I'm afraid, a little bit complicated, but I love them because they're just down the road in Cambridge. And we are only supporting no STD mode. So AArch 64 is the execution mode. Unknown, nobody knows who makes these computers, and none means no specified operating system. The Rust standard library, as it turns out, as many good things are, is 3 standard libraries in a trench coat. libstandard is the top part, and that's the one that interfaces with the OS. So that's the bit that knows if it's Windows, Mac, or Linux, and that's the bit that gives you file system access, networking, and threading. Underneath that, you have the allocation APIs that contains your vector, your string, your B trees, your memory allocator. That lives in a library called liballoc. And then there, at the lowest level, there is libcore. That contains your result type, your option type, methods on floating point numbers, and a bunch of low-level stuff that Rust needs to in order to operate, no matter what target you have. So libcore is available on all targets, and libstandard is only available where operating system support has been written. And liballoc is optional. It's usually available on most targets, and you can opt in. So with this target, it's only going to work in no STD mode, so no standard library, but you do get libcore and you can opt into liballoc. And you might think this is an unusual one. You might think, well, surely you should have gone with ARM Cortex-M for embedded and IoT. Well, again, we were driven by our lead client's requirements. That was the platform they wanted to use. I can't tell you what for, but they wanted big, powerful ARM processor. I imagine they're going to be using an operating system. But I think your path to certification for your product is going to be easier if you don't use libstd, because it's very large and full of a bunch of things you don't care about, because it supports all the operating systems. And you effectively write your own lib standard. You wrap the networking API, you wrap the file system API, you wrap the graphics API, whatever C APIs your operating system provides, you can write Rust wrappers for those, and then you're certifying the bare minimum of code. And I think that's what this client is going to be doing. Because we're on Ubuntu 18.04, we use AArch64 unknown Linux GNU version of GCC as the linker. Yes, it's a Linux linker. That's fine. We can turn off the Linux specific parts. It works fine as a bare metal linker because that's what Ubuntu 18.04 had. We are looking to expand the set of supported linkers in the future. For now, follow the instructions in the user manual and it will tell you how to set things up. And again, if you've got a target, I'm sure there are people out there saying, we really want Cortex-M support. We really want Cortex-R. I know someone is interested in big endian Cortex-R, which is kind of exciting. I know the space industry is big on Spark and RISC-V. I know the automotive industry still loves their Power and Coldfire. All of these things are possible. Reach out, tell us what you need. If Rust already targets that platform, it's a case of running the test suite, which may be a little bit complicated because technically the test suite requires an operating system because it needs to spawn processes and report whether tests are passed or failed. So there's some interesting work we have to do to get the test suite to run for no STD, but we can do that work. So let us know what platforms you want. And if Rust doesn't already target your favorite platform, we can help with that as well. Maybe we can send those changes upstream. So there's a few words about the supported host, 64-bit Intel, Linux, and the supported targets, 64-bit Intel, Linux again, and AArch64, unknown none, bare metal, 64-bit Cortex-A. Now, I want to talk a little bit about the qualification process that we went through for ISO 26262. Quality is a process, right? You can't finish your project and then pour quality over the top afterwards to hide your sins. This is not butter icing to rescue your burnt cake. It's got to be baked in from the start. It's got to be ingrained throughout. And when you build a product according to some quality standards, then it's a process and it works throughout the entire life cycle. And your standard will almost certainly have something to say about every point in your product life cycle. And you may be using a published ISO standard. I know European Space Agency have their own standards from ECSS that they follow for software development. But what we've done is we've chosen ISO 26262 to start. There will be more. At this point, I also want to clarify the terms certification and qualification, because in some domains, these words can be used interchangeably, but when I use them, I have a very specific meaning behind them. So certification is about the process for your product. You are making a product, an anti-lock braking system for a vehicle, engine control unit, industrial control system, the fuel gauge, fuel monitoring system for an aircraft, whatever it is. These are all products and they all need to be certified. You don't get to put those products on the market, use them for their intended purpose, unless you've got a certificate that says they have been developed appropriately and they are sufficiently safe, or whatever other metrics you need for your target market. And that certification process is about your product. And when I say certification, I'm talking about your product. As part of that certification process, you may find there are some I don't want to say shortcuts, but some alternative routes you can take through the certification process if you have tools that are qualified. That is, the tool has been assessed as meeting some elements of your standard, and you can therefore defer some of your certification effort to the qualified tool. You can say, look, I don't need to worry too much about the binary machine code that comes out of my compiler because my compiler is qualified. And therefore, we know the source code to machine code conversion is correct. So therefore, as part of my certification, I can now rely on analyzing the source code because I can trust that source code to machine code works correctly. If you didn't have a qualified toolchain, then you couldn't do that. And you would probably have to look at inspecting and certifying the machine code instead. ISO 26262 is specifically about series production road vehicles and the safety related electrical and or electronic systems within it. And it talks about the hazards caused by malfunctioning behavior. So this is the automotive standard. Pretty much any piece of software that's going to be in your car will have been developed according to this ISO standard. And on the subject qualified tools, it says this, the standard provides a means for the qualification of software tool when applicable in order to create evidence that the software tool is suitable to be used to support the activities or tasks required by this standard, i.e. the user can rely on its correct functioning. And if you're familiar with these standards, you'll know they're all about the activities and the tasks. They'll have big flowcharts of things you must do in a certain order. And having a qualified toolchain can be a step along that path. But having done this, having qualified the tool, maybe you don't need ISO 26262 qualification. You would just like the warm, fuzzy feeling that comes from knowing you have purchased a toolchain which has been through a very rigorous test suite. And we know when the test suite is not sufficient and there's a language spec. We've joined all these things together. So maybe you're not even building certified products, but having this tool chain, having Ferrocene, may be useful to you. Because we can give you confidence. And getting confidence in the tool chain is about three things. It's about knowing what the tool does. It's about checking it does what it is supposed to do. And then it's about proving to someone else the first two items. In terms of what Ferrocene is supposed to do, Rust does not have a written language specification. So we wrote one and we published it. It's open source, it's online. It is the Ferrocene language specification, lives at spec.ferrocene.dev. We can dive in and we can go and look at scalar types. Then we've got Booleans, we've got integers, we've got sequence types. Look, it's all well specified. And that was something we can then test against. We can say, do integers work as we say they work? Do all the various other language features work as stated? The Rust project already had a very good test suite. I don't think it's possible to overstate how good that test suite is. And our work was mainly joining the dots. It was labeling every single test to say which parts of the language specification it covered. And then once we've done that, we can produce the traceability matrix to say, here are all the spec items, and here are all the tests. These tests covered these spec items. These spec items are covered by these tests. Do we have exhaustive coverage of the specification? Yes or no? And to get qualification, we have to prove we have covered everything in the language specification. And we do this in our CI pipeline, and we call this the not rocket science rule of software engineering. Nothing gets merged unless all the tests pass. It's basically a full qualification suite run on every single commit that hits main. And that's just how we roll. And we've been doing that for a long period of time now, and the process works. And then once we've done that, we had to write a safety manual to explain to you, the user of the tool chain, how you can use this tool in a safe and appropriate manner. There's a whole bunch of things you can do with the tool chain that you probably should not. And we can explain those in the safety manual, which command line arguments, which arguments to give to your linker, and so on. Have we managed to convince somebody that this is working correctly? And the answer is yes. We have submitted all our evidence to Tuva. I'm going to move myself down to this corner. So we've sent all the evidence off to Tuva Sud, and they've come back and said, yep, nothing is missing. We are very happy. And as far as we're aware, in fact, no, we got the mail a few days ago. The certificate is in the post. We cannot say it is qualified yet, but it will be as soon as we get that certificate in our email inbox. And they've not just a one and done, they've basically approved the entire process we went through. So we're going to be able to produce subsequent releases, fairly easily. And so what do you get? Well, you can purchase from us the signed documents, so the safety manual, the user manual, and so on. You can get digitally signed assets from us, and then you can present them to your assessor as part of your certification process. I guess that stops people just making their own, get a piece of paper, write on in crayon, this product is ISO certified. You can't just give that to your assessor. There needs to be a chain of trust. And so we can provide you the digitally signed documents when you purchase Ferrocene. But at the same time, we've made it all open source. As I said before, I don't think there's anyone else that is doing this. The source code, github.com, Ferrocene/Ferrocene, and all of the documentations, you can browse them today. publicdocs.ferrocene.dev. There is all the documentation, user manual, safety manual, language spec, how we did the qualification, the traceability matrix. We can go and look at the test suites. So this is not for a specific release. This is for the head of trunk. So I can see that, this is pretty exciting. Someone has made some changes where the test matrix is now showing me that we do not have good test coverage. It's because we continually coming down from upstream. So the tests we've got are passing, but we don't have a fully exhaustive set of tests. That is fixed in the release, and that will be fixed on trunk shortly. But you can come and see the state of play. And if you look at the traceability matrix for the 2306 release, you'll see 100% top to bottom. So that is ISO 26262 qualification. A final few words, if I may, about the support we have available. The source code is MIT and Apache 2.0. The language spec is under the same license, and the qualification documents are all in the repository, and you can look at them now. So how do we get paid? Well, we sell binaries. There are no free of charge binaries for Ferrocene. That is a paid product. You could compile your own if you really want, but we've tried to set the price so it makes sense. You could just get them from us for everyone on your team. We can then also provide long-term support. Tell us about the certified project you are engaging in, and we can tell you how we can support you and get you through that certification process. And as part of that, we can discuss access to the qualification documents which you need for your assessor. We can also talk about third-party crates. We are not currently in a position to say that LibCore has been certified. We understand that is going to be necessary for people to make certified products in Rust. You can't skip LibCore. It's kind of important. And so, we're having a discussion about that with our customers. If you want to get on the certification train, very interested to discuss that with you. So Upstream does a release every 6 weeks, and they will never backport to previous stable releases. We take those Upstream releases and we sort of give them further stabilization, apply our fixes and so on. And that's a Ferrocene release. After 2 years, it goes into extended support where we may not be able to fix bugs. We may just give you workarounds, but we are going to try and give 2 years of support on every Ferrocene release. The numbers in this chart are not correct, but it gives you some sense of what's going on. Upstream produces nightly releases. Upstream then cuts a beta branch every 6 weeks. We've renamed that pre-rolling. And then the Upstream stable we now call rolling. So we have rolling releases of the Ferrocene toolchain available to you. You can have a new Ferrocene toolchain every 6 weeks if you want. Then from the rolling, we cut our betas, and then we have our stable branches. The 2306 release is actually cut from Rust 1.68.2. There may be another 23 dot release this year. We may be looking at a 24 dot something early next year. For the avoidance of doubt, that is year and month in the Ubuntu style. So upstream call it stable, we call it rolling. Upstream call it beta, we call it pre-rolling. And then we introduce our own levels of Ferrocene beta and Ferrocene stable. The source code is free. You can get it from the GitHub. The binaries will cost you 25 euros per month or 240 euros per year per user. Some people say that's unusually inexpensive. Yes, it is. That's by design. We'd like you to just go, well, I'll just buy it for everyone on the team because why not? We priced it to be a no-brainer. And that gives you access to our repository where you can access all of the binary versions or the binary builds of pre-rolling, rolling, beta, stable, all of them, pre-compiled crates we have available. It all comes included. If you want to buy 10 seats or more, we can service you right now. If this was TV shopping channel sales, I'd say operators are standing by to take your call right now. 10 seats or more, we can service you today. If you need slightly fewer seats, you may just have to get in touch and get on the wait list. We need to grow our sales capacity to deal with all this. If you need the support contract and the signed qualification documents, you need to get in touch and we will be able to discuss pricing that meets your exact needs. There is no USB dongle. I have used toolchains with a USB dongle. I do not love them. You will get a username and password to the download area, and you will get a tool for downloading the binaries. Once you have downloaded the binaries, they have no physical restrictions upon them. They are licensed to you, the named user, but you can put them in your CI system. You can burn them to DVD and walk them over to your air-gapped secure network. You could do all the things that you need to do with binaries to make your software. We've designed it with these kinds of software development processes in mind. We can show you a little bit about what that looks like. So here's an example download area. I'm logged in. So I've got my beta release of 2306. The production release will be available as soon as we've got that cert. It's based on Rust 168.2. We've got the last nightly we built, which is on the 9th of October. I think there's a pull request that's currently stopping us that we need to update. Once that's merged, we can start picking up nightlies. We've got our pre-rolling and our rolling release. So 172.1, if that's the Rust release you want, you can have that as Ferrocene. And there it is. And when you click on one of these, there's a list of all of the files. Just click on that tarball, download it and unpack it. And when the critical up tool is available, you can use the command line tool to do basically the same thing. Okay, that's enough for the slides. What I propose is we take a short break and we break at, we return at 15 minutes past the hour. Just gives me a chance to go and grab a drink and set up for the next part. When we return, we will be doing a live demo and I will be live coding some AArch 64 unknown none Rust, and we will be running it in QEMU and we will be using Ferrocene to do that. So I will see you in about 4.5 minutes at 15 minutes past the hour. See you in a bit. Okay, we're back. I've got the terminal ready. We're going to do some live programming. So, how do you get Ferrocene into your machine? If you look at the Y Ferrocene repository, if you clone that, my example is going to be using Docker. So I'm on an Apple Silicon Mac, so I can't natively run the Ferrocene binaries. I am motivated to try and get Ferrocene working on Apple Silicon. But for now, what I could do is I've got a Docker file. So in my Docker file, I just grab all of the tarballs, put them into /temp, and then I extract them all. And then I install some useful dependencies like the AArch64 version of GCC, build essential. I've installed QEMU, and that's it. So it's a pretty straightforward Docker container. And rather than have you watch me build the Docker container, I've got one that I've built already. So here it is. It's running inside an emulator because it's an Intel Docker container on an Apple Silicon machine. And I realize I'm going to have to exit because I'm in the wrong folder. So we're going to go to example 2. There's one I've just created. It's an empty folder. And let's run Docker in there. We go into /work. Right. And so I'm now on machine and I've got Ferrocene installed. So I've installed it into opt Ferrocene. Let's go and have a little look what's in here. It's sort of a standard Unix program. We've got a bin folder. No real surprises there. Cargo Ferrocene self-test is going to go and check that I've got the correct linker available and that some sample programs compile correctly and do the right thing. It's a good way to check that your platform is as required. So there we go. Self-test passed. I've got Cargo, I've got rustc, rustdoc, and the The GDB and LLDB things there, they're actually just shell scripts that wrap your existing debugger. We don't ship a debugger, but Rust GDB loads regular GDB and then loads the Rust plugins just to help with name mangling and printing objects and so on. Not much interesting in lib. There's just some shared libraries. Share, I guess, is the interesting place because that is where the docs live. You've got the standard docs for cargo and Rust C, just the README and the license text. And then Ferrocene HTML is the interesting one because that is where the docs will live for your release. They were in the Ferrocene docs tarball. Go in there, open up index.html. It's going to look like the one available at public docs.ferrocene.dev, but it's going to be the one for your specific release. So that's the one you should be looking at. That's where you're going to find your safety manual, your user manual, your language specification, and all of that stuff is going to be in wherever you've installed Ferrocene, share doc Ferrocene HTML. Then I go into my work folder. Let's make a cargo new bin. I'm going to call it hello. Cargo run. Yeah, using a qualified toolchain, not that different to using a regular Rust toolchain. It's just Rust C. It's just been built with care and supplied with some extra docs. I should note, cargo is not qualified. Rust C is qualified. The build system is big and complicated and can do all manner of things, downloading packages from the internet and so on. So Rust C is the qualified part. And if you want to produce certified software, you probably want to be driving Rust C manually, so you know precisely what it's going to build and how it's going to build it. In the future, we may look at doing a sort of a build plan runner where we can use cargo to generate a build plan and then have a much simpler tool to execute the build plan. For now, you could just do it using calling Rust C with a shell script, and we'll see an example of that. So I need to edit some of this text. And what I'm going to do is I'm going to attach to a running container with this instance of VS Code. That's really neat. If you've never seen that, you can connect to Docker containers using VS Code. So here we go. I am now connected to the work folder in my container, and there is my program. Rust Analyzer is going to run in the background. So this is the Ferrocene demo. Always worth checking you connected to the correct container. Hands up anybody who's spent ages debugging a thing only to find they were editing the wrong source code and they were not modifying the binary they thought they were modifying. Yeah, it's happened to me before. So there we go. Work hello down here is this binary here in our VS Code. Good. Okay. There's a couple of things we need to do to make this a bare metal binary. We're going to mark it as being no std. So we're going to turn off the standard library and we're going to say no main because Rust is going to look for a main function that's written in Rust. And we're not going to do that. We're going to do something different because this is bare metal 64-bit ARM. And I need to write a no mangle extern C function. So this now has C compatible linkage. The name is not mangled, so the linker can see it. And we're just going to jump from K main into our regular Rust main, which I'm going to get to return a result. And that's going to go okay like that. And if this happens to return an error, I can't do print line anymore because I've got no standard library available. But there we go. That's a good place to start. Now, we need to build this in 64-bit ARM mode. So let's make a cargo folder and let's make a cargo config. And we want to set our default build target to be AArch64 unknown none. And so now if we cargo build, complaining we don't have a panic handler. Good. It's clearly done something different, right? It's clearly now gone and built it in AArch64 mode. It's a good point. Let's write ourselves a panic handler. We need a function that looks like this. And let's just put an empty loop in it for now. Actually, no, well, let's put a correct exit in. Because I know I'm running inside QEMU, which is an emulated machine, what I'm going to do is I'm going to exit the emulator by doing a halt instruction with the argument F000, where X0 contains the value 18 hex. Look it up in the ARM specification. There's an ARM spec for how you escape emulators. It's called semi-hosting. You could use it for opening files and printing things, or making the emulator exit. And the ARM specification for semi-hosting on this platform says do that instruction with that argument in X0, and the emulator will exit. So we can go panic. Oh no. It's just going to ignore the panic message. But that should now be a binary we can build. Unreachable, panic, oh no. Expected struct panic. You know what I've done? Panic is not a function. Panic is a macro. There we go. That looks better. Unreachable expression. Boom. Bunch of linker weirdness. What do we immediately think when we get a bunch of linker weirdness? We probably did not configure our linker correctly. In fact, what linker is it even trying to use? Scroll up, scroll up, scroll up. It's trying to use CC. It's trying to use my C compiler as a linker, but it's using the wrong C compiler. It's using an Intel C compiler to link my AArch64 binary. This is not going to work. You have to go and read the safety manual, or the user manual, I think in this case, and it explains you need to give a bunch of arguments to your linker. When you are in AArch64 unknown none mode, use this version of GCC as your linker, and tell Rust the linker is GCC. Give it the argument -f freestanding, give it the argument -no stdlib, and give it the argument this, and this means use linker.ld as your linker script. Now we should be using the correct linker, and the linker says I cannot open linker.ld. Good. Let us fix that. So there is linker.ld, and we're not going to go through how GNU LD linker scripts work. There is some memory at this magic address. There's lots of it. My startup code goes first. We'll come to that in a minute. Then goes my code in text. Then goes my data, which is non-zero initialized. Then goes my zero initialized data. I throw a bunch of other stuff away, and I make a symbol that points to the top of stack. Good. We have managed to link a binary, but the binary won't run. In the debug folder, there it is. Hello. It's a suspiciously small executable because it's the linker's garbage collected everything. There was no startup code, so there was nothing that ever called kmain. So kmain gets deleted, and there was nothing called main, so that got deleted, and then there was nothing calling the panic handler, so that got deleted, and the entire binary ends up empty. To fix this, unfortunately, on this platform, you have to write some assembly code. It is not possible to boot this chip using C or Rust. You can boot a Cortex-M in pure Rust. Yeah, sort of. But this chip, you definitely have to use assembly. So let's make a boot.s file like this. Boot.s. And yeah, we're going to have to do a bit of assembly. So it's going to go in the text startup section. We're exporting a symbol called _start. We're going to set the stack top by taking that symbol, putting it in the stack pointer register. We then need to turn on the FPU. Otherwise, I found out the chip very quickly faults with an FPU exception. So turn on the FPU, clear this interrupt bit, and now we can run kmain. And if kmain exits, we can loop forever, or I guess we could also do hlt f000, we could do mov x0 ox18. So there we go. So we will exit the emulator if we drop off the end we manage to return from kmain. So if we build this now, I am expecting a binary to actually have some stuff in it. No, it still doesn't. I put the source file there. We didn't assemble the assembly file. We didn't link the object into our binary, so nothing has changed. How do we do that? Two options. One, we could manually assemble it into put it in a library and then pass it as an argument, but it's a bit easier if I use a build script to do the work for me, because then it's going to run every time I do a build. Build.rs file executes at compile time. What am I going to do? Get the name of the linker and swap GCC for AS and swap GCC for AR to find the assembler and the archiver. We're then going to take our linker script and we're going to put it in an output directory as given by the environment variable outdir, because while it's finding the linker script at the moment, because we are doing the build in the root of this project and the linker is looking in that folder for the linker script, when you start using workspaces or you do builds where you are not currently at the root of this crate, the linker can no longer find the linker script. So the best solution, and the solution the Rust Embedded Working Group use, is to take the linker script and put it in the target folder somewhere and then set the linker search path so it knows to look there, and then it will definitely find the right linker script. So we take the linker script and we just dump it into the output directory. This is basically a Rust file copy, and we set the linker search path. We then do a process command new on the as command, and we give it boot.s, and we tell it to create a boot object. And then I catch all the various ways the assembly process can fail. We then run the archiver, and we convert our boot object into libboot.a. It's very simple, one object in the archive. And then here's the magic. We tell Cargo, give an argument to Rust that tells it to link against a static library called boot. The GCC as a linker knows that a static library is called lib something.a. So we tell it to link against boot, and it will find libboot.a, which we have placed in the output directory, which is in the linker search path. So now if I save that and we do a build, Rust Analyzer is running in the background. So there's our build script running. And now we have produced a binary with some stuff in it. And we could run it in QEMU, and I think QEMU is just going to exit. Rather than typing out the QEMU command every time, what we can do is add an extra line to our cargo config like this. And so now every time I type cargo run, it's going to execute QEMU with these arguments. The last argument is -kernel. That then gets followed by the elf file we just built. So we can now do cargo run. There it is. It ran and it immediately exited. That's not terribly exciting. How are we going to get some output from our system? Well, to do that, let us make ourselves a struct uart, which contains the base pointer, which is a mute u32, like that. And then let's do impl uart, and we want some new uart0 method, which is going to make a uart. And I'm going to do fill struct field, yeah, and it is ox. We get the right address. That address as star mute u32. This is a perfectly safe. I can construct any number of pointers. Constructing a pointer, not an unsafe operation. What's unsafe is dereferencing it. And then I'm going to write a putchar method, which takes some mutable reference to self, and it takes some byte, which is a u8. And we now have to do an unsafe operation, and we are going to do self.base write volatile u32 from, as I want to 32-bit value, byte. And I know that in QEMU, the transmit data register is the first register at this block of memory. So this is going to work. If I want to do a read char, then it would be base pointer +4. I think there's various ways you can write to UART. This one is going to work. But that's fine. That's bytes. How are we going to print a string? Well, we're going to want to import core format write for UART and Rust. Get Rust Analyzer to do the completion. Yeah, I've got some missing methods. Implement missing members, please. Cool. And then we're going to say for B in s.bytes, self.put char B. And then, okay, we don't need to wait for space in the FIFO, and we don't need to do handshaking RTS, CTS, because this is not really a UART. And whenever the emulated processor puts a word in that address, it's immediately going to appear on the console, so we can take some shortcuts. But now we've implemented core format write for UART, we can do this. Let mute u equals UART new UART 0, and we can change this print line to a write line with u, and I'm just going to unwrap the errors because we don't expect it to fail. And we get an error that says you cannot call a method on this object because the trait is not in scope. So that's fair enough. I'm going to do use core format write. By bringing the trait, I'm now able to do write line. It correctly spots that we can't get to the last line of the code. And let's put something in the UART handler as well. So in the UART handler, I'm going to create a second UART object. It's not great to have two UART drivers going at the same time. On the other hand, a panic is an unrecoverable error. So everything's gone wrong and the world is stopping. So we might as well do something. You know, this is sort of best effort, really. Where's the hash key on a Mac keyboard like that? And I'm not going to unwrap it, because if the write-lin did fail, it would generate the unwrap would cause a panic, which then re-enters this panic function, and you just end up recursively calling panic and using up all of your stack. So make sure your panic handlers can't panic. Oh, and I need to tell it what object I print. This is so nice. I didn't even have to build that. Just red underlines tell me exactly where I'm going wrong. It's just like compiling regular Rust. This would work perfectly well on a standard Rust compiler, except I'm not sure if standard Rust gives you the 64-bit ARM bare metal target pre-compiled. You might have to compile it from source, which means you might need nightly. But it's Ferrocene. So this target is first-class supported target. Do a cargo run. Boom, there we go. So some text has appeared on the UART, and then our panic handler printed out the panic. This is the joy of Rust. We get all of the structured formatting, all just comes built in. As I said, libcore has not currently been certified. If you want to build a certified product, get in touch. We're going to have some very interesting conversations about, can we certify all the formatting machinery? Do we have to give you a much simpler version of write line that doesn't do all of this complicated stuff? That is a question I look forward to solving with our customers. One final thing, we use cargo for this, but I said cargo was not qualified. So instead, you could just write a build script. We're going to go into target production. We're using AArch64 Linux GNU as the prefix. There's my C compiler, there's my assembler, there's my archiver. When I call rustc, use this target, use that linker. There's those linker arguments given straight to rustc. I tell it to look in the target directory for my pre-compiled stuff. And then I'm going to assemble boot.s into boot.o, archive it into libboot.a, compile it, giving the right addition for this crate. There's the crate I want to link against. I'm doing op level S in this case. And then we're going to generate a map and an ASM file. And this is perhaps how you might like to plus x build.sh. And that is going to then assemble and build. As I said, all of this example code is in the Y Ferrocene repository, github.com, Ferrous Systems, Y Ferrocene, so you can check it out for yourself and have a play. Okay, that is the end of demo time. We've built a 64-bit binary. It is running. So let's stop the screen share. Let's go full screen so you can see me. And we've got around 20 minutes left available in the session. You can hang around for as long as you like, and I am happy to answer any questions. So we have one question in the chat. It says, can you recommend a profiler for performance optimization in Rust? Yeah, good question. So I guess this is about profile guided optimizations. If the compiler gets a sense of how your code is being executed, it may be able to make different decisions about the machine code it generates. Is it better to generate small machine code that fits in a cache, or is it better to unroll loops and generate more machine code? Maybe an unrolled loop will go faster. Normally, when you compile your code, the compiler, so it's LLVM, is generating the machine code from the intermediate representation it's given. It does its best guess. I believe LLVM has some profile guided optimizations, so that may help you get code that runs faster. That's probably not going to work on the bare metal targets, though, because the bare metal targets, how do you get the information out of the running program to show what's executed and how many cycles it took? Maybe if you were able to run it inside an emulator, that would be an interesting one. My colleague Andre has put this tool here. So Andre is recommending FlameGraph. Let's have a look at that. Let's go to that link. This is kind of how we run our trainings, by the way. We get interesting ideas. FlameGraph -rs. FlameGraph. There we go. It looks like a good Rust project. So when you so this is using the LLVM performance monitoring stuff, and you can produce graphs like this that show precisely which part of your code is taking the most number of cycles to execute. So that's probably going to work great on Linux, where you can generate all sort of the profiling data and save it out to disk, and then it will post-process that and produce these kinds of graphs. So yeah, that's a really good shout out. I like that. But as I said, on an embedded system, that's going to be kind of a difficult thing to do, perhaps. My stock answer for these kinds of questions is, how would you do that in C? Because Rust is just LLVM at the bottom. So if you can do it in Clang, if there's sort of some sort of Clang plugin that will do the thing you want, then it may well be possible to do a very similar kind of thing in Rust. And if you could do it in Rust, you could probably do it in Ferrocene as well. Okay, well, we can leave the call open for a few more minutes to see if we get any further questions. Not seeing any come through on the chat. If you want to follow up, then you can reach out through ferroussystems.com, reach out through the contact page. Here's a great question about medical device software. Yeah, no, I used to work at a company where we made ISO 13485 compliant medical device development. And yeah, ISO 62304, yes, I think is the ISO standard for software as part of that medical device development process. It's on the list. We will be led by our customers. If you reach out through the contact page and say, here's a project, we'd really like to do it in Rust. Tell us about how that's going to work. We can absolutely look at standards. We're focusing on automotive because that's what our lead customer wanted. And then we did industrial 61508 because the assessor basically said, it's pretty much the same as 26262. You might as well do both at the same time. But for sure, if you've got a need for that, get in touch. We could absolutely look at doing that next. I don't imagine it's going to be a massive delta over what we needed for automotive. The same for DO178C. Spoke to a bunch of aerospace companies recently. That's something they're very interested in. That's something we can look at, but we will be driven by our customers. So customers need to get in touch, say, we're interested in this kind of project. This is what we need from you. So yeah, that's the plan. We've done the work for 26262. We've shown it can be done. You can make a qualified Rust toolchain, and the way we've done it, the approach we've used with the language specification and the test suite and the traceability matrix, we believe is fairly applicable to other relevant standards as well. So for ISO 13485 and things like that. But that's a piece of work that's going to need to be done. Maybe there will be some future Ferrocene releases where we have multiple qualification certificates available. That would be a great place to be. Okay. As I was saying, if you've got any further questions, please do reach out via the website, ferroussystems.com. Go to the contact page. I know contact forms on websites seem weird. You're like, oh, I don't know where that's going to go. They go straight into our company chat. So we absolutely see all the messages you send via our website. That's the best place to reach out. Tell us what you want to do and so on. Let's take another question about, are there any plans to qualify a tool that makes C and C++ interop easier, like cbindgen and CXX? So those do not produce machine code. So does it make sense to qualify them? You could, to show that the input and the output match, do the right thing. Maybe it makes more sense to simply look at the Rust code that's generated and then certify that Rust code as if you had handwritten it. But yeah, for sure, we know that people are interested in using bindgen and cbindgen. CXX is a tool that lets you connect Rust code and C++ code by auto-generating some C bindings. So the Rust is lowered to C and then elevated back up to C++ on the other side, and vice versa. And the bindings are all automatically generated. So yeah, if that's something you need, get in touch. We can look at that. But because that's not going to be part of your final binary, they're sort of code generators. Yeah, interesting question is whether it makes sense to look at qualifying those, or whether it's easier as part of the certification story to just look at the outputs of those tools as source code. Okay, yep, so it's all available. Help yourself. Source code is there, documentation is there. You can read the safety manual. As I said, 25 euros per month per user, 240 for the year. I hope it makes sense to you, and I hope we hear from you soon. So, okay, we will end the stream there. Thank you very much for all of those who've joined. I hope it's been useful. My name's been Jonathan Pallant, and this was Why Ferrocene. So, thanks very much, everyone. Goodbye.